Bismillah ar-Rahman ar-Rahim. In this video, I discuss two important inequalities in probability. The first one is the Kolmogorov maximal inequality. We have a sequence of independent random variables, x1, x2, x3, and so on. These random variables are zero mean. Each random variable has a finite variance. The variance of random variable xi, where I is a positive integer, is sigma I squared, which is a finite number. All those random variables have a finite variance or second moment. Define Sk to be the sum I from 1 to k xi. The Kolmogorov maximal inequality is for every positive epsilon, the probability of the event that the maximum of the magnitude of Sk, so this is Sk, with k in the range from 1 to n, the event of interest is that this maximum exceeds the given positive number epsilon. We want to derive an upper bound on this probability. The upper bound is the sum of variances of the random variables from x1 to xn. So this will be sigma 1 squared all the way to sigma n squared divided by epsilon squared. Sk is the sum I from 1 to k xi by the linearity of expectation. The expectation of the sum is the sum of expectations, and the random variables are zero mean, so this summation is zero. Sk itself has a mean of zero. So the second moment of Sk, which is the same as the variance of Sk, is the variance of this sum. Because of independence, the variance of the sum is the sum of variances. So the variance of Sk is summation I from 1 to k sigma I squared. This means that this summation that appears in Kolmogorov's maximal inequality is the variance of Sn, which is the second moment of Sn. To derive this inequality, we define the following events. Event A sub 0, the magnitude of Sk for every k in the range from 1 to n is less than or equal to epsilon. This is the event A0. Event A0 is the complement of the event of interest. The event of interest is that maximum of magnitude x1 plus x2, magnitude x1 plus x2 plus x3, all the way to magnitude of x1 plus x2 to xn. We want that the maximum of those magnitudes to be strictly greater than epsilon. Event A0 is the complement of this event. No one of those magnitudes is above epsilon. All of them are less than or equal to epsilon, which means that the threshold, the positive real number epsilon, is never exceeded. For integer k in the range from 1 to n, the event ak is that magnitude of s1 is less than or equal to epsilon, magnitude of s2 is less than or equal to epsilon, magnitude of sk minus 1 is less than or equal to epsilon. All those sums have a magnitude that is less than or equal to epsilon. So magnitude x1 is less than or equal to epsilon, magnitude x1 plus x2 is less than or equal to epsilon, and this continues all the way to k minus 1. So the magnitude of x1 plus x2 to xk minus 1, this is also less than or equal to epsilon. But the magnitude of sk is above epsilon. Thus, the sum of the samples or observations from x1 all the way to xk in magnitude exceeds epsilon. This is event ak. If k is 1, it means that the magnitude of s1 is greater than epsilon, which is the magnitude of x1. The event a2 is that the magnitude of x1 is less than or equal to epsilon, but the magnitude of x1 plus x2, this is strictly greater than epsilon. The event A3 is that the magnitude of x1 is less than or equal to epsilon. The magnitude of x1 plus x2 is less than or equal to epsilon, but the magnitude of x1 plus x2 plus x3, this magnitude is strictly greater than epsilon, and so on. Note that the event of interest, that the maximum of magnitude sk, integer k, is between 1 and n, this maximum is above epsilon. This is simply equivalent to the union of k from 1 to n ak. If the maximum exceeds epsilon, then it may be the case that the magnitude of x1 is greater than epsilon, or the magnitude of x1 is less than or equal to epsilon, but the magnitude of x1 plus x2 is greater than epsilon. Or what we have is that the magnitude of x1 is less than or equal to epsilon, the magnitude of x1 plus x2 is less than or equal to epsilon. However, the magnitude of x1 plus x2 plus x3 is greater than epsilon. Or we may have that all the magnitudes are less than or equal to epsilon, and it is the last magnitude when we collect n samples and compute the magnitude of x1 all the way to xn, that in this case we exceed epsilon, but all the previous sums have a magnitude that is less than or equal to epsilon. The event of interest is basically the union of ak, where k is from 1 to n. Those a's are mutually exclusive. If a1 is true, if this event is true, then the other events are false. The first event a1 is equivalent to the magnitude of x1 exceeding epsilon. All the other events they require that the magnitude of x1 is less than or equal to epsilon. So if a1 is true, a2 is false, a3 is false, and so on. If a2 is true, then a1 is false, and a3 is false, and a4 is false, and so on. These events, one of them is true, and the others are false. Note that the meaning of event AK is that the given positive real number epsilon, the threshold, is exceeded for the first time after we construct the sum based on the samples from x1 all the way to xk. So it is with those samples that we are able to make the magnitude of the sum above epsilon. Using the samples from x1 to xk minus 1, this didn't happen. The probability of interest that we want to upper bound is the sum k from 1 to n, the probability of ak, which is the probability that ak is true. Below, I use indicator ak. This is 1 if ak is true, 0 otherwise. And the probability that ak is true, which can also be written as probability ak, is the expectation of the indicator. The indicator is two-valued, 0 or 1. The expected value of the indicator is 0 times probability ak complement plus 1 times probability of ak. So the probability that ak is true is the same as the expectation of this indicator, which is like a Bernoulli random variable, and the probability of success is that ak is true. AK is true, again, means that the threshold epsilon is exceeded for the first time when we use the sum from x1 all the way to xk. This is the inequality that we want to prove, and we have this sum here, which is the variance of Sn, or the second moment of Sn. Now, this sum of variances, let's write it in this way. It is the second moment of Sn. Let's introduce inside the expectation the sum k from 0 to n indicator ak. Note that this summation is exactly equal to 1. This is a sum of the indicators of the events a0, a1, all the way to an. a0 is the complement of the event of interest. The threshold epsilon is never exceeded. And the union of those other guys is the event of interest. The probability of the event of interest is the sum of those probabilities here. Going back to our derivation, we take expectation of Sn squared. It is expectation of Sn squared times 1. And I will take this one and write it as sum k from 0 to n, indicator ak. One of those events is true and the others are false. If a0 is true, the threshold is never exceeded. If a1 is true, the threshold is exceeded for the first time after collecting the sample x1. a1 just means that the magnitude of x1 is above epsilon. a2, the threshold is exceeded for the first time after collecting two samples or measurements or observations. Magnitude x1 is less than or equal to epsilon. Magnitude of x1 plus x2, this is greater than epsilon, and so on. One of those indicators is 1 and the others are 0. The sum is equal to 1. By linearity of expectation, we can apply expectation to the random variable Sn squared times indicator ak. And we have a summation k from 0 to n. We are summing the expectation of non-negative random variables. We can lower bound by eliminating one of those non-negative terms. And what we will do is that we will eliminate the term corresponding to k equals 0, and our summation now will start from 1. So rather than having a sum from 0 to n, and this is an equality, now we have greater than or equal to, and the sum is k from 1 to n. And then we have the expectation. Inside the expectation, we have Sn squared. Recall that Sn is x1 plus x2 all the way to xn, and then indicator ak, which is 1 if ak is true, 0 otherwise. The second step is to take this Sn and write it as Sn minus sk plus sk, like this. Then we will expand the square. We will take Sn minus sk as one term and sk as another term squared. We have three terms, Sn minus sk squared, and then we have sk squared, and then we have double sk times Sn minus sk. Let's examine the three terms that result after expanding the square. This term here, we will not be interested in doing anything to it except to note that it is a non-negative term. It is the expectation here. Inside the expectation, we have the square of Sn minus sk, and we have the indicator, which is either 0 or 1. And so this is a non-negative quantity. And this is enough for our purposes. Then we have this expectation here. Let's leave it for a while. Let's talk about this expectation. So when we apply the expectation, we have expectation of, we have this Sn minus sk, and then we have this sk, and then let's not forget the indicator ak. What is Sn minus sk? Sn is the sum of the random variables x1 plus x2 plus xk minus 1 plus xk plus 1, and then we go all the way to xn. What is sk? Sk is x1 plus x2 all the way to xk. when we subtract sk from Sn, then we have a summation. And this summation is I from k plus 1 to n xi. Sn minus sk is a random variable that depends on xk plus 1, xk plus 2, all the way to xn. What about sk? Sk is the sum from x1 to xk. And what about the indicator? Indicator ak. The event ak is the event that the threshold is exceeded for the first time after collecting the measurements from x1 to xk. How do we know whether event ak is true or false? How can we know with certainty that ak is true or false? What are the members of the sequence x that will tell us whether this indicator is 1 or 0? The claim is that we just need to know x1, x2, all the way to xk, and that's it. When is this indicator equal to 1? When is event ak true? Event ak is true if and only if the magnitude of x1 is less than or equal to epsilon, the magnitude of x1 plus x2 is less than or equal to epsilon, all the way to the magnitude of x1 plus xk minus 1 is less than or equal to epsilon, but then the magnitude of x1, now if we include xk, the magnitude exceeds epsilon. If those inequalities are true, event ak is true and this indicator is 1. If we have any violation, then this event is not true and the indicator is 0. What is of concern to us here is that the event ak depends on the random variables from x1 to xk, and it's independent of the random variables xk plus 1, xk plus 2, all the way to xn. The current situation is that this random variable Sn minus sk depends on the random variables xk plus 1, xk plus 2, all the way to xn. On the other hand, this random variable sk, indicator ak, depends on the random variables from x1 all the way to xk. Since the sequence x1, x2, x3, and so forth is a sequence of independent random variables, then these two random variables are independent of each other. The expectation of the product can be written as the product of expectations. I can write down this as the expectation of Sn minus sk times the expectation of sk indicator ak. Now, this expectation is the expectation of this sum here, and this is the sum of 0 mean random variables, so this expectation is equal to 0. This other expectation, we are not interested in its exact value. We just need to know that it is a finite number because this expectation is upper bounded by the sum I from 1 to k of the expectation of magnitude xi, and those are finite numbers because our random variables, they have a finite second moment, and so they have a finite first moment and a finite absolute first moment. 0 times a finite number, this is 0. This is 0, and this is greater than or equal to 0. Now we can take this sum of the variances and lower bound it by this summation here. Claim sk squared indicator ak is greater than or equal to epsilon squared indicator ak. Why is this true? Let's see. We have two cases for the indicator. The indicator can be 0 or it can be 1. If event ak is false, then the indicator is 0, and we have the inequality 0 is greater than or equal to 0, which is a valid inequality. If ak is true, we have that the magnitude of S1 is less than or equal to epsilon, all the way to the magnitude of sk minus 1 is less than or equal to epsilon, but the magnitude of sk is greater than epsilon. If ak is true, both indicators are equal to 1, and we have all those inequalities. Those inequalities include this inequality that the magnitude of sk is greater than epsilon, which means that sk squared is greater than epsilon squared, which implies that sk squared is greater than or equal to epsilon squared. So this will be a true inequality. We can lower bound this quantity here, sk squared times indicator ak. This is greater than or equal to epsilon squared times indicator ak. Epsilon squared is a constant, so it can be taken outside the expectation and the summation. Here it is. And we are left with summation k from 1 to n, expectation of the indicator. Well, that's the probability of ak, the probability that ak is true. And we have agreed that this summation of probabilities here is exactly the probability of interest. We have this summation is greater than or equal to epsilon squared times the probability. So the probability that the maximum of the magnitude sk, integer k between 1 and n, the probability that this maximum exceeds epsilon is less than or equal to the sum of the variances, which is the same as the variance of Sn divided by epsilon squared. Now let's move to our second inequality, the Hàjek-Rènyi inequality. We still have the sequence of 0 mean independent random variables. Each one of them has a finite variance, specifically variance xi is sigma I squared. We have the same definition of sk. So everything is like Kolmogorov's maximal inequality, but now we have those new guys. Those are positive real numbers in non-ascending order. We have ck is a positive real number for every positive integer k, and we have that C1 is greater than or equal to C2, greater than or equal to C3, and so on. The event of interest is not just the magnitude of sk exceeding epsilon, it is the magnitude of sk multiplied by the constant ck. And we have the maximum k now, rather than starting from 1. In some applications, we need to start from something other than 1. So k now is an integer in the range from m to n. Why do we introduce ck? In many applications in probability, we are not just interested in the sum of random variables. We are interested in the sum divided by a power of n. Let's say divided by n. One typical use of those constants is to choose ck to be 1 over k. In this case, ck times sk is equal to 1 over k summation I from 1 to k xi. This is the sum of the first k x values from x1 to xk divided by their number. And this is the quantity of interest in something like the strong law of large numbers. To give us the flexibility of having the sum of the random variables scaled in a certain way, we will introduce those constants here. Now we will define our events. The A events are like in the previous inequality. I will define event A sub m minus 1. This is the event that the threshold is never exceeded. This means that Cm and then the sum x1 all the way to xm is less than or equal to epsilon. Then Cm plus 1 and then the sum from x1 to xm plus 1 is less than or equal to epsilon. This continues to Cn times the magnitude of the sum from x1 to xn also less than or equal to epsilon. So this event Am minus 1 is the complement of the event of interest. This is the event that the threshold is never exceeded. But for integer k from m to n, the event ak is that Cm magnitude Sm is less than or equal to epsilon all the way to Ck minus 1 magnitude Sk minus 1 less than or equal to epsilon, but Ck magnitude Sk is greater than epsilon. Here, Ck times the magnitude exceeds epsilon for the first time if we use our observations from x1 all the way to xk. To do this proof, we will need another set of events. The event Bm minus 1 is an event that is always true, so the probability of Bm minus 1 is just 1. For integer k from m to n, the event Bk is defined in this way. It is Am complement intersection Am plus 1 complement all the way to intersection Ak complement. So event Bk is true if all the events from Am to Ak are false. This definition of the events Bk will allow us to write down the indicator Ak as the difference between these two indicators, indicator Bk minus 1 minus indicator Bk. And this will be needed in the proof of this inequality here. Let's first justify this statement. Recall that indicator of an event is 1 if the event is true and 0 otherwise. We have two cases. The first one, what if event Ak is true? If Ak is true, which means that the threshold is exceeded for the first time by using the samples from x1 to xk, then Bk is false. If Ak is true, then by definition, Bk is false. If Ak is true, this indicator is equal to 1. And now, by definition, Bk is false and this indicator is equal to 0. Recall from our previous discussion that if Ak is true, then no other A is true. So if Ak is true, which means that the threshold is exceeded for the first time using the measurements from x1 all the way to xk, then the events Am plus 1 all the way to Ak minus 1, all those events are false. And by definition, Bk minus 1 will be true. Indicator Bk minus 1 is equal to 1. And yes, 1 is equal to 1 minus 0. So if Ak is true, this identity here is verified. What if Ak is false? In this case, this indicator, so Ak is false. Now this indicator is equal to 0. Now if Ak is false, let's look at Bk minus 1. It is Am complement intersection Am plus 1 complement all the way to Ak minus 1 complement. What is Bk? Bk is Am complement intersection Am plus 1 complement. Then we have intersection Ak minus 1 complement, intersection Ak complement. Now, if Ak is false, then Ak complement is true. And these two guys are exactly the same. They are true together or they are false together, depending on events from Am to Ak minus 1. These two indicators now are of the same value. They are either both 0 or both 1. And in the two cases, the indicator of Ak is 0. So this identity is true. Indicator Ak is indicator Bk minus 1 minus indicator Bk. Consider the summation k from m to n, expectation Ck squared, Sk squared, indicator Ak. Like what we did in Kolmogorov's maximal inequality, Ck squared, Sk squared, indicator Ak is lower bounded by epsilon squared indicator ak. Why is this true? Well, the indicator can take one of two values. If ak is false, indicator ak is equal to 0, and we have 0 greater than or equal to 0, which is a very fine inequality. If ak is true, then both indicators are equal to 1. And what does it mean that ak is true? Ak is true means that Cm magnitude Sm is less than or equal to epsilon. Cm plus 1 magnitude Sm plus 1 is less than or equal to epsilon. And we have Ck minus 1 magnitude Sk minus 1 is less than or equal to epsilon, but Ck magnitude Sk, which is Ck magnitude of the sum x1 all the way to xk, this is above epsilon. If ak is true, it implies that Ck magnitude Sk is greater than epsilon. So Ck squared Sk squared is greater than epsilon squared, which implies that Ck squared Sk squared is greater than or equal to epsilon squared. This quantity here is lower bounded by epsilon squared indicator ak. We can take the epsilon squared outside the expectation and outside the sum. And the sum of the probabilities, ak is true for k from m to n. This is exactly the probability of the event of interest. We have shown that the probability at maximum, then we have integer k from m to n of Ck magnitude Sk exceeding epsilon. This is upper bounded by epsilon to the minus 2, and then this summation here. In order to finish off the proof, we need to show that the summation is less than or equal to this quantity here, which involves the constants C1, C2 all the way to Cn and the variances. So this is now our goal. If we show this inequality, then we are done. Take this summation and write down the indicator as indicator of bk minus 1 minus indicator bk. Now we will find a use for the events bk and split the sum into two sums. So the first summation will be summation of expectation ck squared sk squared indicator bk minus 1, and then we have minus, and then we have the same summation, but now we have indicator bk. And the second sum, I wrote it with the index j. The next step from this summation, isolate the term corresponding to the index k equal to small m. And from this summation, isolate the term with the index j corresponding to small n. So from here, we will have cm squared, recall that the c's are constants, and then expectation sn squared, and then the indicator of bm minus 1. And by definition, this indicator is equal to 1. From here, we isolate the term corresponding to j equal to m. We will have minus cn squared, and then we have expectation sn squared indicator bn. This summation will start from m plus 1. This summation will be summation j from m to n minus 1, expectation of cj squared sj squared indicator bj. We do a change of summation index. Specifically, we write j as k minus 1. When j is equal to m, then k is equal to m plus 1. And when j is equal to n minus 1, then k is equal to n. And every j here is replaced by k minus 1. The two sums, they have the same range. The index is from m plus 1 to n. So we can recombine these two sums as this summation with expectation. We have indicator bk minus 1, and then we have ck squared sk squared minus ck minus 1 squared sk minus 1 squared. To repeat, we start with this summation. Write down the indicator as the difference of these two indicators. Now we make use of the events bk. Split the summation into two sums. From the first sum, isolate the term corresponding to k equal to m. From the second sum, isolate the term corresponding to j equal to n. Then do change of summation index. Recombine the two sums again. Note that this term here, because event bm minus 1 is defined to be an always true event, then indicator bm minus 1 is 1. And this is cm squared expectation sm squared. And this is cm squared. And then we have the sum of the variances from 1 to m sigma I squared. We want to upper bound. And here we have this term here with the minus sign is less than or equal to 0. So we can just remove it and have less than or equal to. And then we have this sum. Recall that the constants C1, C2, C3, and so on are in a non-ascending order. We have C1 greater than or equal to C2 greater than or equal to C3, and so forth. This means that Ck minus 1 is greater than or equal to Ck. This means that we can square both sides and we have the same inequality. Now, if we multiply both sides by minus Sk minus 1 squared, then the inequality will be reversed. We have this inequality here, Sk minus 1 squared. I can upper bound this by minus Ck squared Sk minus 1 squared. Now, Ck squared becomes a common factor and it can be taken outside the expectation. Sk minus 1 is the sum from x1 to xk minus 1. Sk is the sum from x1 to xk. So Sk is just Sk minus 1 plus Sk. the difference between these two squares is sk squared plus 2 times xk minus 1. If we apply expectation to this sk minus 1, after accounting for the indicator, we encounter a situation like what we have seen in deriving Kolmogorov's maximal inequality. We have expectation xk, but then we have sk minus 1 and then indicator bk minus 1. What is sk minus 1? This is the sum x1 plus x2 all the way to xk minus 1. What is indicator bk minus 1? This is 1 if bk minus 1 is true. What is event bk minus 1? This is am complement intersection am plus 1 complement all the way to ak minus 1 complement. What are members of sequence x that we need to know so that we are certain whether the event bk minus 1 is true or false? We just need to know x1, x2 all the way to xk minus 1. We can check event am is true if we have that cm times the magnitude of the sum from x1 to xm, this is greater than epsilon. Am plus 1 is true if am is false, which means that this inequality is negated, and we have that cm plus 1 times the magnitude of the sum from x1 all the way to xm plus 1 is greater than epsilon, and so on. We can know for sure whether this event is true or false if we have access to the random variables from x1 to xk minus 1. That's it. The random variables xk, xk plus 1, xk plus 2, and so forth, they give us no information whatsoever regarding this event here. Thus, this product is a random variable that depends on the random variables from x1 to xk minus 1. What we have here is xk, which is independent of those guys, because we have a sequence of independent random variables. And so the expectation of the product can be written as a product of expectations. We get expectation xk, and xk is a zero mean random variable. 0 multiplied by a finite quantity gives 0. This term here is equal to 0. What about this expectation here? The indicator is upper bounded by 1. This expectation is upper bounded by the expectation of xk squared, which is the variance of xk, which is sigma k squared. This summation here is upper bounded by the sum k from n plus 1 to n, ck squared sigma k squared. And this is exactly what appears here in the upper bound.